Today we're going to talk about Ka and how you calculate the pH of weak acids, ones that partially dissociate. Now here, you're going to have to go over these two equations, okay, and use those on a regular basis, okay, so get used to memorising those, okay, and we're going to talk about weak acids. So weak acids dissolve in water and produce hydrogen ions, but they're partially dissociated. So that means the equilibrium is mainly over to the left. So we've got a lot of this, and not a lot of this, and not a lot of the conjugate base, the A-. Now we can convert this into an equation called Ka. Now Ka is equivalent to Kc, so it's Kc when it comes to acids. So that still means it's products over reactants. And the products here are H plus, A-, divided by HA, which is the reactant. So that converts into this. So it's literally just a Kc equation, okay, but in terms of acids. So we replace the C with A and A. So there's our products divided by our reactants. Now with all other constants, the position of the equilibrium depends on the strength of the reaction itself, the rate of reaction, and in this case, the strength of the acid, because if it's partially dissociated, it's going to be this direction. If it's fully dissociated, more that direction, and somewhere in between. Might be a little bit here, a little bit there, okay? But it's the same as every other Kc, for example, or the rate equation. It only depends on the change in temperature in terms of its change. So it'll change because of the temperature, but won't change because of anything else. So remember, constants in your A levels only change when it comes to temperature. Okay, now in this case, a really important point is that Ka remains the same for each acid. So Ka remains the same for each acid. So if you're given an acid, you're given a Ka value, you can assume that is the same throughout the question, or if you change the concentration. That Ka will only change if you change the temperature. Okay, that's really, really important. Now we're going to go straight into the calculations of the pHs of weak acid. And you see again, we've got the equation right here. You can see we've got the Ka value here. Now, we have to make two very important assumptions. Now, these really important assumptions mean that you can calculate it really, really easily, okay, but you've got to remember both of them. Now, when it comes to the assumptions, if you're a big maths person, the answer for most weak acids will still be exactly the same whether you make the assumption or not. So the assumption just basically makes the calculation easier. So the first assumption is that your concentration of H plus that you produce is equal to the concentration of your conjugate base. Okay, so the concentration of your H plus is equal to the concentration of your conjugate base. Now, if that's the case, and you do that, you know that the number in the Ka equation here is the same as the number here. So that means we can square it. And I'll show you later. Now, the next one is you assume the weak acid is not dissociated, as in you assume this is not dissociated at all. So these two assumptions kind of counter each other, which means that if you didn't make the assumptions, you still get the same answer. Okay, so they kind of cancel each other out. So assume the weak acid is not dissociated, therefore, okay, the equilibrium HA is the undissociated. So basically the number here that you're given right at the start doesn't change. You can take that number for the concentration and you can put it straight down there. So you can square that number is the first one. Okay, and so let's have a look at it. There we go. So you can square the number, okay, and you can just put the number from the equation. Now this probably doesn't mean that much. So let's put it into a question. So the question here is calculate the pH of 0.1 moles per decimeter cubed aqueous ethanoic acid. Now, there's different parts to this. There's different parts. So the different parts are, first of all, what's the Ka expression? So you might be asked in an exam, what's the Ka expression? Now, the Ka expression is relative to the acid that you've got, and we've got ethanoic acid. So what we can do is we can start off by just doing the Ka expression. It's always good to do the Ka expression. So H plus, you look there. So we do H plus, and we do it in the square bracket. And then we times it by our conjugate base. Now, our conjugate base is relative to ethanoic acid. Now, H plus taken away from ethanoic acid leaves CH3COO minus. Okay, so it's got CH3COO minus. Now, if that's the case, you divide, because you've got the divide here. Okay, and we've got the acid there, and again in our square brackets. So we've got the full acid here. So we've got conjugate base, H plus. Now that's an expression, and that will get you marks in the exam. So if they ask you to write an expression for Ka, you've got to do that. You can't just write Ka equals H plus squared divided by HA. That's not the expression. It must be relative to the acid that you are given. Now, if that's the case, we now want to do the calculation itself. So I'm just going to move the question over to the side now. Okay, and we will do the calculation. And let's not forget our equation. Now, if we're doing this, we can start off with the numbers. So the number is 0.1, and we've been given a Ka, which is really, really nice. So what we can do is we can rearrange this. Now, I'm going to rearrange this for you, just in case you're not sure. So Ka, I'm going to take this up. So that's going to be times by CH3COOH. Let's make that a proper 3. Okay, so that's that. I've just moved that up. Okay, and then remember that, and I'll just write this over here, because of your assumptions, you're saying Ka equals H plus squared over HA, and HA is this. So we've brought that back up, and then to get rid of the 2, the square, we've just got a square root. So what we do is we square root here, and that will equal our H plus. And if you get used to doing that, and you get used to doing that square, let's make that square root a bit more obvious, then actually it's not too difficult a question. So if we put that in, and we know that concentration of the ethanoic acid was 0.1, if the concentration is 0.1, okay, HA at the start is the same at equilibrium. Okay, so this number right here is our HA. Okay, so all we do is go 0.1. Okay, and then we look at the Ka value, 1.74 times 10 to the minus 5. So 1.74 times 10 to the minus 5. Okay, and then what we do is we take that entire lot, and remember, we square root it. Let's make our square root really obvious. There we go. That's all I've done. Okay, and that will equal our H plus, which is here. So our H plus, when we do it, is going to be 1.319 times 10 to the minus 3. Okay, and that is in moles per decimeter cubed. Okay, so that's our hydrogen ion concentration. Then all we do is we take our equation up here and we go, right, okay, let's try a different colour now. Okay, which will be pH. I'm going to look at minus log of H plus. Okay, and there you go, minus log of H plus. And then from there, we will just put in 1.319 times 10 to the minus 3. Okay, and that is our concentration. Okay, which gives us a final answer of 2.88. Really remember, really important, to 2 decimal places. Okay, always to 2 decimal places when it comes to pH. So that is your pH, and that is how you do a simple calculation of pH of a weak acid when you're given the concentration. We're now going to introduce Ka and pKa. Now, Ka and pKa have a relationship very similar to pH and H plus concentration. So you've got 2 acids here, and you've got the Ka values of each of those. Now, remember, the larger the Ka, the stronger the acid. That's because you get more dissociation. Remember, it's a product divided by reactants equation. So therefore, out of the 2 here, the one that is the strongest acid is the one with the largest number. So we say this is the one with the largest number. So sulfurous acid is a much stronger acid than hydrogen peroxide. Now, this is an exam answer. Sometimes they'll say, why do you use pKa? Now, what pKa is going to do is change it into a more manageable number. So Ka can span a really wide range. You can see the wide range from -2 to -12. So it's a really wide range. So this will then make it so that it's manageable, smaller range. Okay, and that can be asked in an exam. So the connection between the two is pK is the minus log of Ka, much like pH is the minus log of H plus. Okay, and then Ka is 10 to the minus pKa. So you've got 2 different equations here. Now, if we look at those two equations and then we look at some data and start to see some patterns. So the data here we've got some pKa values and we've got some Ka values. So if I stand here, you can see pKa, that is increasing. And you see Ka here is decreasing. So let's put the arrows there. So that's getting bigger. Okay, and that's getting smaller. But they're the same acid. So that basically, and we know from the Ka values that the stronger the acid, the higher the Ka. So the higher the Ka, the strongest acid here out of these three is going to be the biggest number. The biggest number is 5.62 times 10 to the minus 4, hydrofluoric acid, okay? Now, the opposite is with pKa. The higher the pKa, the weaker the acid. So the biggest number here is 10, so it's the weakest acid, so the strongest acid is the smallest number. And that's done by this minus log, so it inverts it basically. It says something that has a high number will then have a low number afterwards. And that basically is how you can tell the difference between a strong acid and a weak acid with Ka and pKa. So we're going to go through a couple of ways in which you might use pKa instead of Ka. And the first one is acid-base pairs. So if you haven't talked about acid-base pairs, you can look at those in a previous video and previous video on acids. So just go back to the one Bronsted-Lowry and pH of strong acids and you'll see something in there. Okay, now, if you are going to do it, what you need to do is you'll be given two acids and you'll be given the pKa values or the Ka values, depends what it is. And you have to use those to determine which one is the stronger acid. So we have determined, right, that the lower the pKa, the stronger the acid, right? So if we've got two there, the lower number is the stronger acid because it says pKa, it doesn't say Ka. So that means on this one here, we're going to say this one is stronger. Okay, so that's stronger. So that's how we do it here. So what we do is we start writing out the equation. So we've got C6H5COOH. Okay, so we've got that. And we add it to ethanoic acid. Okay, so we've added it to ethanoic acid. We know that the benzoic acid is the stronger one. So this is the stronger one. The stronger one is going to donate its proton. So it's going to donate its proton. Right, now, really important, the proton goes on anything that's electronegative. Okay, so you don't put the proton on here. You can see here we've got H on an O, also it will go on there, it makes sense. And so you normally put it on something that's electronegative and also usually where there's a H already, so an OH or an NH or anything like that. So that means the ethanoic acid is going to act as a base and the benzoic acid is going to act like an acid. So if that is the case, we're going to make this, we're going to make it donate a proton. So that's then donated a proton. That proton is then going to be added on to this. So I want to add it on. So I'm going to put 2. And if I add a proton on is a plus. So I have to put a plus on the end there. Now I have to do acid-base pairs. No, acid-base pairs, basically an acid, we know this is acting like an acid. So this is acting like an acid. So we're going to call that A1. Okay. And then what's connected to it is its base. So if it goes back in that direction, so if we did this as a reversible arrow, for example, if it goes back in that direction, okay, it would take the proton back off, okay, and it would accept that proton, which means it would be a base. So I'm going to call that base, and they're paired together, so I'm going to call that base 1. Then I'm going to go for this one, okay. This is accepting the proton on this side, so accepting the proton to go for there. So that's going to be a base, and it's the second pairing, so I'm going to put base 2. And then I'm going to put acid 2, because if this goes back the other way, it's going to donate the proton, act like an acid. Okay, so that is how you use pKa to write an acid-base pairs type question. So we're now going to calculate the pH of a weak acid, but using the pKa value. Now the pKa value is going to be using these equations, okay? So these equations, so we've been given the pKa. You can't really do anything in A-levels with pKa particularly, okay? You have to convert it to Ka to then do something with it. So therefore we're going to use this equation, 10 to the minus pKa. And feel free to do this without waiting for me, okay? It's a bit boring watching the video and not doing anything, so stop the video, try and do it. Okay, so Ka is equal to 10 to the minus, that's 3.75. Okay, so that's 3.75. If we do 3.75, that is going to be equal to 1.77. I'm going to put 3 dots because I'm going to keep that number in the calculator. Really important that I keep it in the calculator. And that is times 10 to the minus 4. Okay, so we've got that number. We're now going to use this equation. Remember, that is shortened to Ka equals H plus. Because of our assumptions, okay, we can do this. Okay, so we can just square it. And then we rearrange that. And if we rearrange that, it's Ka, let's put it down here. That's Ka times Ha, and that's a square root, and that's H plus. And we can work out our H plus from there. Okay, so if that's the case, if we want to do our H plus is going to be equal to 1.77. And this is our Ka value that we're doing here. And that is times 10 to the minus 4. And that's HA. HA says 0.05. And if we take a square root of that. Okay, so we've got our equation, we've got H plus. And that basically means if we've got H plus is going to be equal to 2.98 times 10 to the minus 6. And again, I'm keeping it in my calculator. Really, really important. Keep it in your calculator. Okay, don't round. Okay. If that's the case, we then go to the last stage. And last stage can be pH equals minus log of H plus concentration. So pH is going to be equal to the minus log, okay, and that is of 2.98 times 10 to the minus 6. Again, in your calculator, kept in your calculator. Use the answer button. Get used to using the answer button. All right, if that is the case, we should have a pH at the end of it of 2.53. And again, it is to 2 decimal places. Okay, and there you have how to get the pH from the concentration of a weak acid, and it's pKa. So the next type of question is to calculate the pKa for the acid. Trying to twizz it all around and move it all around. And again, let's make sure you have those equations up in the corner. Okay, so we need to calculate the pKa. To get the pKa, we have to calculate the Ka first. Okay, so one of the tips is make sure if you're given a pH, you change that into H plus straight away. That means I've got my H plus and I've got my HA, which means I can calculate Ka, and then from Ka, I can calculate my pKa. So let's do this. Again, stop the video. Don't wait for me to do it, okay? Just stop the video and do it yourself. So pH, okay, is equal to 4. So if I go to, and then I go to 10 to the minus pH, 10 to the minus 4, okay? And if I go to 10 to the minus 4, that is equal to 1 times 10 to the minus 4, okay? So I'm not including units anywhere here, just because of space and things like that, but that is moles per decimeter cubed. Now, if that is the case, and you've got that, you've got 10 to the minus pH. Remember, 10 to the minus pH is equal to your H plus. So I've got my H plus, which means I've got my H plus to go in there now. Okay, so all I then do is Ka is equal to H plus. Remember, we assume these are both the same concentration, so H plus squared. Okay, and that means 1 times 10 to the minus 4, and that's the concentration, and that's squared. Okay, so square that, and then we have to divide it, because HA is up here, 0.1. And then that equals, do a different colour, 1 times 10 to the minus 7. Okay, and that is your Ka value. So you've got Ka, so we can put Ka in there. and then we can put pKa. So, because our final answer is our pKa. So pKa is minus log, and it's 1 times 10 to the minus 7, which is wonderful because it equals a very nice number, which is 7. And it's a pKa, so you don't need to do it to lots of decimal places and things like that. It's a whole number, so that's nice. If it had decimal places, obviously report it to 3 sig fig, usually 2 decimal places. And that's how I get a pKa from pH and HA concentration. So we're going to go a very seldom asked question, but this could be the difference between an A star and an A. Okay, and that is the limitations of using approximations for this. So the approximation, both of the approximations are that you assume that the H plus equals the A minus, and therefore you can do H plus squared, and you assume that this doesn't change. So the original concentration is the equilibrium concentration, so you just use the number. So you've got 2 approximations. Now they work in the majority of substances until you get something called a stronger weak acid. So for around about pHs 2 and 3 and things like that. It doesn't work in these, and it might ask you a question why it doesn't work. So an example might be this. So carboxylic acid is generally weak, but this one's a little bit stronger. Okay, and you use the approximation. So using approximations of Ka value and a H plus value here, and then squaring the H plus, okay, in your calculations you can get a pH of 0.76. Now that's really quite strong. Okay, the actual pH is 0.26. Now, those different values means that the approximations you make, which is again, this is the same concentration, this doesn't dissociate, it's only for stronger weak acids, okay, that means they don't work. So otherwise this number would be the same. The pH with the calculation would be the same as the actual pH with a pH meter. Okay, so if that's the case, okay, remember those approximations, you assume that the weak acid is not dissociated, therefore that equals that. So therefore, if a question asks you and says, well, why does this not work? Why is this the case? It's because this can't be true. So if this can't be true, as the pH is lower, so more HA must have dissociated, or in this case, 1,1-trifluoroacetic acid. So if basically for a stronger weak acid, you are told in the question that the pH that was calculated with the approximations is not the same as the actual pH, it must mean that this assumption is not correct, and therefore the equilibrium is more to the right, therefore some of the HA must have dissociated, okay, more than it does in the approximation, okay, and here is your answer for this question.